Today we are going to be looking at recurrence relations and mathematical induction through the game played by children called the Tower of Hanoi, which is a bunch of discs of decreasing size going upwards that you move between various poles. Apparently legend has it that this task was given to some monks in Hanoi, and they had to move 64 of these solid gold coins, and when they've completed moving them from one pole to another, the world will end. Well, fortunately, as we shall see, moving 64 discs according to the rules would take 585 billion years, so we don't have to worry too much about that. Okay, but anyway, let's have a look at the rules first. The rules are quite simple. You can only move one disc at a time. There's a disc there, a bigger disc there. You can only move a top disc, so you can't move that disc, for example. You can only move the top one, and you can only put a disc on a smaller disc, i.e. you can't put you can't put this disc here on top of the smaller disc there. So the rules are relatively simple, and basically what we need to find out is what is the minimum number of moves to move the entire stack from one pole to another. Okay, so basically let's have a look. We just need to do a couple of little definitions here. So let's say that there are n discs, and let's say that the number of moves to move the n discs is mn, and that's what we want to find. Okay, and we're going to use recurrence. So what we're going to do is we are going to look at the n-1 discs, i.e. basically every disc except the one at the bottom. And how are we going to move all n discs? Well, what we're going to do is we're going to move the n-1 discs to there, then we're going to move the bottom disc to there, and then we're going to move the n-1 discs to there. So basically, how do we move all n discs? The minimum number is equal to, well, it's equal to the number of goes it takes us to move n-1 discs across to that pole, plus 1, which is moving that bottom disc across there, plus the number of goes it takes us to move the n-1 discs across there, which is plus n-1 again. And that equals 2m(n-1) add 1. And we have here now a recurrence relationship, namely mn equals 2m(n-1) add 1, which we can solve. Now, in order to solve this, we need to know what m1 is. Well, obviously, if there was only one disc here, the number of moves it would take us to move that disc from here to here is only 1. So we know that m1 is 1. And now what we've got to do is we've got to solve this recurrence relationship. And what I'm going to do is I'm going to do it in an informal manner today, because obviously this is supposed to be a fairly light-hearted video. So let's have a look. So we basically have mn is equal to 2mn-1 add 1, which means that mn-1 would be equal to 2mn-2 add 1, and mn-2 would be equal to 2mn-3 add 1, etc, 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 i.e. mn equals 2, replacing this with mn-1 would give us 2mn-2 add 1, which equals 2 squared n-2 add 2 to the 1 add 1, and mn also equals, if we replace mn-2 here, it would give us 2 times 2m(n-3) add 1, which equals 2 cubed m(n-3) add 2 squared add 2 to the 1 add 1. So we can see that basically the pattern is going to be mn is going to be equal to, once we've finished all this and we go all the way down to m1, it's going to be equal to 2 to the power of n-1 m1 add 2 to the n-2 add 2 to the n-3 add 2 to the 1 add 1. So that's basically what it's going to be, and we know that m1 is 1. We've already established that. So basically mn, i.e. the number of moves to move an n high pile of discs from one peg to another, is equal to the sum, that's mn, sorry, it's equal to the sum between r equals 0 and n-1 of 2 to the r, which is a geometric series. First term is 1 and the ratio is 2, and therefore the sum is equal to 1 times 2 to the power of n-1 over 2 minus 1. That's just the sum of the n terms of a geometric series, and so therefore mn is equal to 2 to the n-1, i.e. the minimum number of moves to move n discs here. So if we have n discs here, the minimum number of moves to move n discs from here to another pole is 2 to the n minus 1. So if there were 2 discs, for example, it would be 3 moves. If there were 3 discs, for example, it would be 7 moves. And for our monks, it would be 2 to the power of 64, take away 1, which is an absolutely extraordinarily large number. Even if they moved 1 a second, it would take them billions of years to move the 64 discs, according to the rules, from one post to the other, so we don't need to worry too much about that. Okay, now in actual fact we can also prove this by mathematical induction, so let's just do that. So basically let us assume that mn, so we need to prove, sorry, that mn equals 2n minus 1. Okay, well we need to first of all do the base case, which is m1. Well, m1 clearly is 1. We know that's 1. It takes 1 move to move one disc from one pole to another. And if we put that in there, that equals 2 to the power of 1 minus 1, which equals 1. So it's correct for the base case. Now, secondly, we have to assume that it's true for n equals k, i.e. we assume that mk, i.e. the number of moves it takes to move k discs, is equal to 2 to the k minus 1. And then 3, what we need to do is we need to show that for n equals k plus 1, that mk plus 1 equals 2 to the k plus 1 minus 1, i.e. to move k plus 1 discs would take us 2 to the power of k plus 1. And so let's have a look at that. Well, let's just have a look at our 3 pegs here, and let us imagine that we have our k plus 1 discs here. How are we going to do that? Well, we are going to move k of them across to there, and then we are going to move the bottom disc across to there, and then we're going to move the k across to there. So mk plus 1 is equal to mk add 1 add mk, which equals 2mk add 1, and we've already assumed that mk is 2 to the k minus 1, so therefore m to k plus 1 is 2 times 2 to the k minus 1 add 1, which is 2 to the k add 1 minus 1, which is what we needed to show. And then number 4 on our induction, all we need to do is put the conclusion, which is to get the extra mark, as true for n equals 1, the base case, and as true for n equals k plus 1, assuming true for n equals k, assuming true for n equals k, then by mathematical induction, it is true, and we prove the statement. Okay, so that basically is doing it using those 2 methods. But now what we're going to do is we're going to do a restricted Tower of Hanoi. Okay, so this is slightly different. It's basically exactly the same rules, but let us imagine that you can only move 1 peg. So in the first one, remember, what we did was we moved n across 1 peg, but then we moved the bottom one across 2 pegs. Well, let's imagine you can't do that. You can only move any disc 1 peg. So you can't move from A to C. You can only move from A to B or B to C or whatever, right? So now let's have a look. How many moves would it take to get all discs from peg A to peg C? We want to know what Mn is. So Mn we're now defining as the number of moves to get all discs from A to C, but moving only 1 peg at a time. 1 peg at a time. At a time. Again, we're going to do this by a recurrence relationship. So what we're going to do, let's have a look at the same idea. There's the n minus 1. So what we're going to do, in order to work out how to get the n discs from A to C, remember that's how we're defining Mn, is the number of moves to get all discs from A to C, is we're going to move n minus 1 discs from A to C, and then we're going to move the bottom disc to B. And then what we're going to do is we're going to move the n minus 1 discs back to A, and then we're going to move the bottom to C, and then finally we are going to move the discs back from A to C. Now basically it will be a 2-step process. We can't move the n minus 1 directly from A to C, but we can use in our recursion, in our recurrence relationship, how many moves does it take to move them from A to C, even though we know that they're all going to have to go via B. Just out of interest, what we couldn't do is move the n minus 1 discs to B and leave them there, because then we'd have nowhere to put the bottom disk. Remember, the disks can only move one at a time, so we have to move all n-1 to B, and then we have to move all n-1 to C, and then we move the 1 to B, and then we can move the n-1 back because the biggest one is on the bottom. Then we have to move them back again, then we move B there, and then finally we can complete it. Okay, so let's have a look. So basically what we said there is the number of moves to move the n from A to C, remember, is going to be the number of moves it takes to move n-1 across to C, add 1, which is moving the bottom one to B, add the number of moves it takes to move them back from C to A, add 1 again, which is moving the bottom one from B to C, add mn-1, which is finally moving them back from A to C again. And so that gives us that in this recurrence relationship, we have that mn, which is moving them from A to C with only one peg allowed to be moved each time, is equal to 3n-1 add 2. There's our recurrence relationship there. Okay, so basically we can use the same idea that we just used. We're going to use it informally to solve this. Mn is 3n-1 add 2. Mn-1 is equal to 3n-2 add 2. Mn-2 is equal to 3n-3 add 2, etc. So completing it in, and again, I know there are more formal ways to solve these recurrence relationships, but let's do it this way because it's nice and clear, makes it clear what's going on. So mn equals 3. Let's stick mn-1 in here. 3mn-2 add 2 add 2, which equals 3 squared n-2 add 3 times 2 add 2. So mn, now sticking mn-2 in, that gives us 3mn-3 add 2 add 2 add 2, which equals 3 cubed mn-3 add 2 times 3 squared add 2 times 3 add 2. So basically we can now see the pattern there. We basically now know that the pattern is going to be mn is equal to 3 to the n-1 m1 add 3 to the n-2 times 2 add 3 to the n-3 times 2 add add 3 times 2 add 2. Now we just have to be a bit careful with what m1 is. I'm not sure I've mentioned what m1 is. M1 is if there's only one disk. How many moves does it take to move one disk from A to C, given that we can only move to an adjacent disk, adjacent peg? It takes 2. So M1 is 2. You have to move it first to there and then to there. So M1 is equal to 2. And so therefore Mn is equal to 2. We can take 2 out as a factor. 3 to the n-1 add 3 to the n-2 add 3 add 1. And that basically equals the geometric series where A equals 1 and R equals 3 this time. So that equals 2 times 1 brackets 3 to the n-1 over 3 minus 1, which is 2, and the 2 cancels, which leaves us with 3 to the n-1. So this time, the number of moves it takes under the new conditions, where you're only allowed to move one peg at a time, the answer is 3 to the n-1. So it's far more difficult than the previous one. So if these monks in Hanoi had to do it using these rules, it would have, I don't even know what 3 to the power of 64 is, but it's a lot bigger than 2 to the power of 64. So they were lucky that they only have to do it 2 to the power of 64 times, and it takes 500 billion years. So let's have a look, proving this by induction. Okay, so we need to prove by induction mn equals 3 to the n minus 3 to the n minus 1. Okay, well the base case we've just discussed is m1 equals 2, which equals 3 to the power of 1 minus 1, which is 2. Okay, so the base case is fine. Then let's assume for n equals k that it's true. Therefore we assume that mk equals 3 to the k minus 1, and we need to show that for n equals k plus 1, that mk plus 1 is 3 to the k plus 1 minus 1. So let's just have a quick look at our 3 pegs here. So we got the n plus 1 here. Basically what we need to do is we need the mk, which is moving them across there, add 1, add mk, add 1, which is the base one, add mk again. So basically we have, oops, sorry, just running out of space here. So basically we have that mk plus 1 equals mk plus 1 plus mk plus 1 plus mk, which is 3mk add 2, and we've already established that we assume that mk equals 3k minus 1 per our induction, so therefore mk plus 1 is equal to 3 times 3 to the k minus 1 add 2, which is 3 to the k plus 1 minus 3 add 2, which is 3 to the k plus 1 minus 1 as required. And then we need to write our conclusion, remember, basically, which is that as it works for the base and as it's true for n equals k plus 1, assuming true for n equals k, then we prove by mathematical induction. And that is what we needed to prove there. Okay, and so therefore we're done. Well, look, I hope you found this interesting, our little Tower of Hanoi problem. If you have, please like this video and subscribe to the Gresty Academy YouTube channel. Thank you.